All right, y'all. We're now at part two of the trophic levels lecture. We're going to continue on talking a little bit about energy flow through ecosystems, but this time we're going to talk a little bit more, focus a little bit more on that idea of energy transfer and how we lose energy as we move up through those trophic levels and what impact that has on ecosystems. Okay, so remember we had talked a little bit about this idea of primary productivity, particularly net primary productivity, being the basis for all the energy in an ecosystem. So when we start thinking of that as, okay, here is a set amount of energy that can move through that ecosystem, we can arrange this as a kind of like a pyramid, because the pyramid has a broad base, and as you get higher up, it gets smaller and smaller as far as the width goes. And this kind of represents the number of individuals that can survive in an ecosystem or in a specific area based on what those trophic levels are. Okay, so you always have to have a wider or a larger number of individuals than the next lower trophic level to support that trophic level. So there has to be a lot more autotrophs than there are herbivores. There has to be a lot more plants than there are herbivores out there in order to support all the herbivores, because again, we don't see energy being transferred very efficiently, and so on and so forth as you move up. So that's what this diagram kind of represents, is the change or shift in energy as it moves from the base of that ecosystem or from those primary producers up to some of those higher level consumers. Okay, and this again is because of that idea of the second law of thermodynamics, that a closed system or a system tends to have an increase in entropy. In other words, a loss of that energy or that energy moving or leaving the system. Basically because there's energy is not transferred 100%. A lot of the energy is lost as heat. Okay, so we lose heat. When you run, your body heats up. That is some of the energy that you are not able to convert from carbohydrates into ATP that gets lost as heat. That's because it's an inefficient system. Okay, and that's kind of a similar sort of thing that we're talking here. It's not just heat that's being lost or things like that, but it's the inefficiencies in moving energy from one trophic level to the next. Plus, remember, the difference between gross and net, that you have to use some of that energy just to maintain yourself. Okay, not all of the energy that you consume is going to be available for the next trophic level up. Okay, so if we start at that base and say, okay, we've got solar energy coming in, it's hitting the Earth's surface. From that amount of solar energy, photosynthesis happens. And again, this is that first energy transfer from inorganic to something that's organic. Okay, now we like to think that, hey, plants are really good at it. They're actually pretty inefficient. It's estimated that somewhere between 1% and 3% of the solar radiation that actually strikes the Earth's surface is actually captured for gross primary productivity. Okay, and more than half of that is used for respiration or some of that maintenance. Okay, which means that our net primary productivity is about a 1% to 1.5% efficiency rate from the amount of solar radiation that's hitting the ground, hitting the Earth's surface, gets actually converted into carbohydrates. That's available in the form of biomass that's available then for primary consumers to eat. Okay, so we can already see that this is pretty inefficient. Okay, so some of that energy that's hitting the plant just can't be absorbed, because remember, we have that light saturation point, or that point at which it doesn't matter how much more light you add, the plant is not going to be able to be able to convert it into carbohydrates or use it for photosynthesis. Okay, a lot of this energy is reflected. Some of it gets transferred as heat. It heats up the leaf. Those kinds of things, all those different things. So anything above that light saturation point isn't converted into net primary or into gross primary productivity. Okay, and again, once we get to gross primary productivity, then the net primary productivity is subtracting out that respiration rate or that maintenance rate, and we get even less of that energy that hits the Earth's surface transferred into carbohydrates. Okay. So again, there's each one of these energy transfers, each one of these shifts from one trophic level to the next, we see a loss of energy. So once we get that sunlight in there, about, let's say 2% of the energy gets transferred into gross primary productivity, 1% gets put into biomass. That means 1% of the energy that hits the earth in the form of sunlight is available for primary consumers to be able to eat. Okay. Now, when the primary consumers eat this, they're eating something, they're processing this energy, they're absorbing this energy, okay? Then they have to use some of that energy for maintenance, for respiration, and the rest of it goes into production of biomass. Okay, well, the amount of energy that's available for those secondary consumers, those carnivores, to be able to eat is only the amount of biomass that's produced by those herbivores. Okay, it's not the total amount of energy that's consumed by the herbivores, because again, there's a difference between the gross amount of energy and the net amount of energy that's available to the next trophic level. Okay, so where we see some of this process happening is, or so loss of some of that energy is, not all of the biomass in one trophic level is eaten by the next level up. So not all of the grass or not all of plant material is eaten by herbivores. There's lots of roots that aren't eaten. There's other parts of the stem or tree that aren't eaten. There's all sorts of different stuff. The bark might not be eaten. That's biomass that was produced that is actually, represents energy to some extent, but it's not consumed by those herbivores. Okay. Next, once they ingest that, okay, so there's total amount of production. There's only a portion of that that gets ingested. Now, once they eat it, okay, then they have to basically absorb that energy. So how much of the energy that is eaten is actually assimilated. Blah, sorry, I just noted I misspelled assimilation. I spelled it assimilatation. So I apologize for that. So it's assimilated. Okay, so you ingest so much energy, not all of it gets, absorbed. We excrete a good bit of our, food that we eat through the process of feces, and that gets passed on through. So that's energy that's still available. There's still energy in there. It's just that we didn't absorb it, so we don't have that much of, the energy that we even ingest gets absorbed into our body and is available for us to use. Then of that energy that is absorbed, okay, not all of it gets put into the production of biomass. A lot of it gets used for respiration and for maintenance. Again, the difference between gross and net. So even when we look at the amount of biomass available in a landscape is in the form of plants, we see that herbivores don't eat all of it. Okay, and then all of the energy that's in that food that they do eat is not assimilated, and then not of the energy that's assimilated gets put into the form into production of biomass. That biomass is then available for those primary consumers, the carnivores, to be able to eat. So this is kind of how we're losing a lot of these. Okay, and as we go through, we see that each one of these steps, there's a level of efficiency. Okay, so how efficient is an organism at being able to eat all the available energy from a particular, from the next trophic level down? How effective of a consumer are you? Okay, are you a really good consumer? Are you able to eat most of all the productivity that's available to you? Okay, and once you've consumed it, okay, your assimilation efficiency. How efficient are you at assimilating the energy that you have ingested? Okay, so how your digestive tract works. How effective is it? How good are you at absorbing those nutrients, that energy? Okay. Once you've assimilated that energy, how good are you at converting that energy into biomass? Okay, how much energy do you need to maintain yourself? How much gets used for respiration of the energy that you do assimilate? And we see, depending on the type of organism, we see variances in these different types of efficiency. Okay, so when you start thinking about how efficient is an organism at being able to make that production, that biomass that's available for the next trophic level, we have to start thinking about how effective they are at consuming things, assimilating things, and then producing things. And at each one of these levels, we're seeing a reduction in the amount of available energy that's being passed on to the next trophic level. Okay? So overall, what we think about is what's that growth efficiency. Okay? So how much of the food that you ingested is put towards production? Okay, this gives an overall effectiveness of how do you go from what you eat to producing biomass for the next trophic level to be able to consume. Okay. All right, so in general, what we tend to see is, depending on which organism or group of organisms you're talking about, there are differences in what those efficiencies are. Okay, some are really efficient at ingesting or at consuming. That consumption efficiency can be really, really good. It can also be really, really low. If you think about large predators like cheetahs, okay, for every time they try, they've got a pretty low rate of capturing prey. So their consumption efficiency is not that great. And other things like cows. Well, yeah, there's a lot of grass there, but cows are pretty daggum good at eating grass. Things like that. In general, when you start talking about it, aside from consumption efficiency, when you start talking about how effective are you at assimilating, we tend to see things like granivores and predators being really, really efficient. And part of that's because of what they're eating. Okay, seeds are really easy to digest. There's a lot of really rich carbohydrates that are there for the plant's embryo that are easy to digest. They're easy to break down because they're there to feed that embryo in that seed. So if you're eating that, it's easily digestible. Okay, if you're eating another organism, if you're a predator, okay, that biomass in the form of another animal tends to be pretty easy to digest. Muscle is not that difficult to digest in comparison to plant material. Plant material is not easy to digest. Remember, we cannot process cellulose. Okay, we have to have some sort of symbiote or some sort of bacterial gut flora that's able to break that cellulose down. And even so, there's just not, you tend to see that things that are herbivores have to eat a heck of a lot of grass, a heck of a lot of plant material in order to get an adequate amount of energy to be able to support them. Okay, whereas, a cheetah may have a bad consumption efficiency because of the fact that it's not able to catch things, but once it catches something, once it eats, what it eats, it's easily able to assimilate a vast majority of that meat that it has eaten, things like that. Okay. Other patterns that we see once we get to that assimilation, within that assimilation efficiency, is we tend to see that homeotherms, so remember we talked about adaptations to temperature, that being homeotherm means that you maintain a constant body temperature, and we think of these organisms as being also endotherms or warm-blooded organisms. We tend to be better at assimilating, okay, because of the fact that since we have a higher body temperature, we're better able to conduct metabolic processes efficiently and fast in order to break down that food that we've eaten and absorb it, as opposed to cold-blooded animals or poikilotherms or ectotherms that aren't as good, because a lot of that depends on what temperature they're at. Okay, they're not able to maintain that constant body temperature, so they may not be that effective at assimilating that energy. Now, on the other end of the spectrum, though, when we look at production, okay, cold-blooded or poikilotherms are way, way, way more efficient at production basically converting what they've assimilated into biomass. Okay, than homeotherms are. Okay, because remember, when we think of homeotherms, we also think of endotherms or warm-blooded organisms. So if you're warm-blooded, you have a really, really high maintenance rate because you're maintaining a constant temperature, which means you're basically fueling a furnace constantly. And a lot of the energy that we consume, even that we assimilate, gets used for respiration to maintain that body temperature. Now, if you're cold-blooded or you are an ectotherm, you're not utilizing that energy that you've assimilated in maintaining that body temperature. So there's a lot more available energy for you to convert into biomass or production. So you tend to see that poikilotherms, aren't great at digesting things, but what they do assimilate, they're really effective at utilizing that and converting it into biomass, which is one reason why you see that poikilotherms or ectotherms generally don't need to eat as much as homeotherms or endotherms or warm-blooded animals. Okay, so it kind of starts getting us an idea or a pattern of what we see with what types of organisms are in an ecosystem as to what types of how much energy starts moving through there. So when we start averaging these things out or thinking of this as in a broader scale, what we tend to see is the range of energy transfer from one trophic level to the next, on average, is about 10%. Okay, so only 10% of the energy available in one trophic level, produced in one trophic level, is available to the next trophic level. Okay, so this puts a real big limit on how many trophic levels there can be in an ecosystem. Okay, very rarely do you see ecosystems with more than 4 trophic levels. Okay, because if you do, then suddenly what ends up happening is you start seeing if only 10% of the energy moves to the next trophic level, you start off with a relatively high amount of energy even at the bottom. And by the time you get to these really high up top predators, and like tertiary consumers, there's really not much energy left from that primary production. So let's say we start off with 100 kilograms of energy, just of biomass, just to give us a number to start with. So if we have 100 kilograms of plant biomass in a specific area, and then suddenly we have herbivores that eat all that 100 kilograms of biomass. They're eating all of it. So we're talking about 100% consumption efficiency, which isn't going to happen. But if we do have that, through that ingestion, assimilation, and production, only about 10 kilograms of production is available for the next trophic level, or those primary consumers. Okay, and if that's the amount of production for those primary consumers, okay, if they eat 100% of, well, we're going to assume 100% consumption efficiency, then what happens is only 10% of that energy is transferred into production among those primary consumers. Okay, I'm sorry, secondary consumers, excuse me, those carnivores, those secondary consumers. Okay, so this is a pretty rapid reduction in the amount of energy that's available, which is why we tend to see that there aren't nearly as many predators in an ecosystem as there are primary consumers, and there's not nearly as many primary consumers as there are autotrophs or primary producers. Okay, if you have a lot of energy, you might be able to get a tertiary consumer. Okay, but that means if you had a tertiary consumer, which would be this red one at the very top, there's only 0.1 kilograms available, okay, or produced, sorry. So they would only be getting 0.1 kilograms of that energy in producing. So it starts to get really, really small as you get higher and higher and up. And you never really see anything above that tertiary consumer, because then you're looking at 0.01 kilograms that would be passed on to the next trophic level. Okay, so this is one reason why that patterns in net primary productivity relate to this different amount of biodiversity that we see. So if you raise that kilograms at the bottom to 1,000,000, then we have a little bit more energy that's moving up. If you drop it down to something really low, you don't have that much energy moving up. Okay, so this is one reason why you don't see a whole heck of a lot of top predators. Okay, because of the fact of that loss of energy. So as you move up those trophic levels, what we tend to see is that there's an increased area that is needed to support fewer number of individuals. Okay, so if you look at things like grizzly bears, they have a home range that's usually between, around 20 to 70 square miles to support a grizzly bear in Wyoming, in that area near Yellowstone. Okay, if you go to mountain lions, again, it depends on the habitat. If it's a really lots of primary productivity, then there's going to be a lot more prey items for it to eat, and it can have a smaller home range, but it can range anywhere from about 30 square miles to about 100 square miles, depending on how much primary productivity or how much available energy there is. If you go to tigers, their home ranges can be up as large as 300 square miles because of the fact that, hey, they need lots of energy. And if you have low amounts of primary productivity, like you have in some of the areas like Siberian tigers or some of the other areas that they live in that don't have high primary productivity, there's not going to be enough energy moving up those levels to support many individuals that are going to be secondary consumers or even tertiary consumers. Okay. So this kind of explains the pattern that we see going from plants all the way up to those top predators, that we tend to see few top predators in a given area, and their density is relatively low. Okay. Now, what we've just kind of gone through is what oftentimes referred to as a grazing food chain, because it starts off with plants and what gets eaten, what do those primary consumers eat as moving up that food chain. But as I said earlier, it's like not at that consumption efficiency. Not all of the leaves are eaten by those primary consumers. Some of those leaves fall off the ground. Fall onto the ground. They don't fall off the ground. They fall onto it. They drop, they fall, and they start to decompose. Or you have sticks and things like that that drop and start decomposing. So again, there's lots of little side chains that are going on in here. All that energy that's available, that's out there, generally tends to get used. Now, this is one of those things that we see that drives evolution or natural selection is, do you find a new source of energy? Do you find a new way to access energy that's not accessible to other individuals? And that's going to carve a little niche for you that allows you to be able to thrive and survive, reproduce, and pass those traits on to the next generation. Okay, so you do see things like detritus food chains where you've got fungi eating decomposing dead plants, and then you've got nematodes eating fungi, and then you've got other things eating nematodes, and eventually you're getting up into birds or insectivores that are eating these things as well. So just different ways to think of that food chain or that trophic level as well. Excuse me. Okay, so yeah, just kind of talking a little bit about those. But the main one that we think of when we think of these trophic levels is that grazer food chain, or that grazing trophic level. We start off with primary producers, then we go to primary consumers in the form of herbivores, then we go to secondary consumers in the form of carnivores, and so on and so forth. Okay, until the energy basically gets too small to support anybody else. All right. Okay, last couple things I want to talk about is, we already mentioned this idea of trophic cascades, where one step or several steps up in the food chain affects things much lower down. We had talked a little bit about that with keystone species. We tend to see things like top predators act as keystone species because of the impact that they have on the prey or whatever, limiting the number of competitors, that's the word I'm looking for, competitors among some of those lower trophic levels. Okay, this is what we refer to as top-down control, this idea that the predators control the prey. Okay, and if those prey are too abundant, then they're going to, start eating up all of the primary productivity and impact how much primary productivity is. But as we've just discussed, there's also this bottom-up control where we look at how much primary productivity there is, controls all those upper trophic levels. So more primary productivity means there's more herbivores, which means there's more predators and those things. Okay, so we see this going back and forth. So there is a mix between these two. The more primary productivity there is, the more trophic levels that ecosystem can support. But at the same time, the lack of a predator, a top predator, can also have a cascade effect downward as well. Okay, that it can impact the number of primary consumers or herbivores that are there, which is going to impact how much of that primary productivity actually gets consumed or survives to the next generation or next season and things like that. So there's this balance or this interaction between this bottom-up control, or how much primary productivity there is, controlling how many individuals in those subsequent higher trophic levels, and this top-down control, where we see keystone species controlling how many competitors and how much competition there is in the biodiversity downwards as well. So I just do want you to understand what is meant by top-down control and bottom-up control, because these are two things that are often discussed as ways to think about how biodiversity is controlled by these trophic levels. Okay, so hopefully that makes sense. This completes our discussion on trophic levels. I want you to kind of understand how energy is transferred, that rate of energy, primary productivity, and net versus gross, what patterns we see in primary productivity, and what impact that has on biodiversity, and those kinds of things. All right, our next lecture will focus on nutrient cycling, and that will be the last set of lectures for the semester. All right, we'll talk to you later.